So yesterday we discussed our first models to describe the epidemic dynamics in a simple, reasonably simple way, and we saw the SIS model, which had as result you have a criterion for the epidemic to happen, which was a certain constant, which is the R0 being bigger than 1. And then what happened with the SIS is it goes to a stable state. Okay, so the disease becomes endemic due to the loss of due to the non-existence of immunity. Okay? Well, then we moved further, and we saw the SIR model with total immunity, lifelong immunity. And in this case, we also find a condition for the epidemic to happen, which is also something called R0 being bigger than 1. This is the condition of which sometimes we call the condition of invisibility. Okay? And what happened in this case was different. It did not approach an endemic equilibrium. At the end, if you go for a long time, the number of infectious persons is 0. So over time, so there is a burnout. The epidemic tends to by naturally go away. Okay? And then we found that also that we could calculate the total number of people that had been infected by the epidemic at the end of the epidemic by calculating the number of people who recovered at time infinity, which was a transcendental equation, but anyhow, something solvable. And then the point about this equation, it depended only on R0. Right? Only on R0. So this could be done because of the characteristics of SIR model, which has no loss of immunity and so on. With SIS, we could not do this because we got to a state where an equilibrium between new infective and people getting out of the effective class. So there are always new infections. So we cannot really calculate the total size of the epidemic in this case, because the epidemic, it never ends. So there is no total size. Okay? So, okay, now we want to take into account something else. We want to take into account in our SIR model, we want to take into account the following. We have considered the population constant. And that's reasonable. Right? That's reasonable because the time scales of variation of the population size is very different from the time scale of the disease itself. Right? So, but there are people being born and people dying. Okay? So, if we still want the population to be constant, we can say that people that are being born and people that are dying kind of equilibrate. So they will sum up to a total population which is still constant, but you have the influx of newborns and you have the deaths of others. Okay? So this is called an SIR model with demography. It's a little bit exaggerated to say that this is really demography, but okay. So how would we write this thing? Okay, so we would write again with dsdt gi dt and g r dt. And well, the epidemic itself, the epidemic terms, would be the same in principle. So you had minus beta s times I over n. Then you would have the influx here of the new infected minus some gamma. I, oh no, not, let me see, just, okay, let me, mu I, just to have the same notation as yesterday, which will then go here, okay? Now, I will make the following. I will consider that there is a constant death rate of the population, which does not depend on the class susceptible, infected, recovered, which means that it is not disease related. It's just the natural death rate the population has. So I will therefore put some death rate, which will be gamma times S minus gamma times I minus gamma times I. Okay? Okay? So that's the death rate. Now the birth rate, okay, will happen that there's no maternal transmission, so we will consider that everybody that is born is susceptible. Okay? Therefore, I need a term here that is positive, newborn, and has to balance this. But the total number, if you add up this, okay, if you add up these equations, what will you get? You will get ds plus I plus r dt, ds plus I plus r dt, which is the total number of the population, which we want to have constant, okay, will be something which this cancels with this one with this, and this is just minus gamma s plus I plus r. Okay? So this is without birth. Okay? So if I want to put birth, I have to add something here as a certain birth rate, which equilibrates with this one, which will be gamma times this guy. Okay? And this guy is just the total population, which is constant. So it's gamma times n. Okay? Yeah, okay with this? So I'm equilibrating, I'm compensating the death with birth in such a way that the population is constant. And if you now sum up this here, then you will have what you had before plus gamma times n, but n is this, so this cancels with this, and this is constant. Okay? So what I have to put here is gamma n in order to ensure that the population is constant. Okay? Yeah?
Professor, in the third equation for r, shouldn't it be minus gamma?
No, it's plus, okay. No, minus.
R. Shouldn't it be r?
Which one?
The last term of the third equation.
Which is this? I'm a R. Yeah, sure. Okay, you're right. So, okay, with this we have the constant population, and let's see what will happen in this case. Okay, I will raise this one. The first thing is we want to find the invisibility criterion, which is which is given by there will be the epidemic if on a totally susceptible population, if I introduce a small number of infective, if it will grow, then I say I have an epidemic. Therefore, I need di dt at time 0 bigger than 0, so positive, so that will grow. And if you look at this, you have beta times I times S over n, but S over n is what? Is 1, because a totally susceptible population. And then you have minus b minus mu minus gamma. That's di dt at t equal to 0, which we want to be positive. Therefore, beta minus mu minus gamma has to be positive. Therefore, beta divided by mu minus plus gamma has to be bigger than 1. And this is R0. Okay. So that's the intrinsic, that's the condition of, to have an epidemic. R0 has to be bigger than 1. And again, if you look, I mean, for every time we write this, you can then think about more or less the interpretation of this can always be referred to the secondary case that the index case produces. So we have the R0, but now, so it didn't change much, yes, from the SIR for the time being, okay? Because, well, you didn't have the gamma, okay? So this was the R0 that we had before, just adding gamma, because, well, because yes. So now we can, however, think about, is there a fixed point at this system, okay? And will the fixed point be stable? In this case, we would have something different from what we had before. So let's look for stable fixed points. Not so fixed points, we can start, let's say, by di dt equal to 0, which will be imply that beta times, I will use this, meaning the fixed point value, over n times the fixed point I minus mu I minus gamma I. Okay. If this is equal to 0, I can cancel the I term. Okay. And I will get that the fraction of susceptibles at equilibrium is equal to gamma plus mu plus gamma divided by beta, which is 1 over R0. Right? Remember. And, okay, this means that this is obviously, if only works if R0 is bigger than 1. Okay? So therefore this is smaller. Because if this is smaller than 1, you don't have the epidemic, and the fixed point would imply that S is bigger than 1. The fraction would be more than the population. It's not possible. Yeah? So then we have gs dt equal to 0, which will imply that which implies that minus beta s star I star divided by n minus gamma s star plus minus gamma plus gamma times n is equal to 0. Okay? So this time I cannot cancel star, but I can substitute it from here. And then I can calculate I over n. Okay? So so you will have minus beta. So this is S is 1 over R0. Okay? So in here we will have I divided by n. Okay? That's just substituting here. Okay? Minus gamma over R0 minus gamma n equal to 0. Okay? Well, in this, if you go and solve this, you will get I over n being just gamma over beta times R0 minus 1. Okay? So this gives you the equilibrium population of infections, which means that the population, there is a fixed point such that the population, that the epidemic has not ended, because there are still infectious people. So there is this is endemic, right? So this is endemic. So this, well, and the fixed point will also have some R, but R I don't need to calculate. I mean, because R is just n minus S minus I, because the population is constant. Therefore, I don't write this. Okay, so it's effectively a system of two equations on it. Okay, these two. Okay? So now, now what we want is that there's I made a mistake here. Yeah, one mistake. The mistake is that there's no n here. Okay, that's it. Okay. Yeah. Minus plus gamma. Okay. There's n. Ah, okay. That no, yeah, n. Okay, that's correct. Okay. Yep. So then you divide by n because you want I over n. Then this n goes away. Therefore, there's no n on the other side. Okay. Oh, sorry. Okay. So, okay. So I have a fixed point. Okay. So now, what we have done in ecology could be done. We can do it here. We just calculate the stability of the fixed point. So I won't do this because, well, it's lengthy and it's a little bit. You need to know all eigenvalues. Okay, but I'm not doing this right now. But what you can show is that this point is stable, provided R0 is bigger than 1. Anyhow, the fixed point only exists if R0 is bigger than 1. So if R0 is smaller, the only fixed point is the disease-free equilibrium. Okay, population is constant, no infection, no recovered. Okay, that's the only point, that the only equilibrium. But when R0 is bigger than 1, then there's a second equilibrium, and it is also easy to show that the disease-free equilibrium is unstable if, well, okay, that has been actually already shown here. Okay. If R0 is bigger than 1. Okay? So I have what sometimes it's called the exchange of stability. I have a stable fixed point. This is the disease-free equilibrium. And when a parameter, which is R0, crosses a certain threshold value, which is 1, this point is not anymore stable. And you have another point which is stable. Okay? And this is not a transition like the ones we discussed last week, which were catastrophic because there was a jump. Okay. Now, when R0 crosses the threshold value 1, this is very close to to 1. This is very, very small. And the equilibrium is very close to the previous one. And then it grows. Okay? So it is just like if you put I over N plot times R0. Okay? This is just 0, and then it goes. That's it. Okay? That would be the bifurcation graph. Okay? So, okay. So this point is fixed, is a stable fixed point, but there is some characteristics that remember predator-prey dynamics, because, well, more or less, this is also a kind of predator-prey dynamics. Yes. So what happens is that the system approaches the fixed points by oscillating. In mathematical terms, this means just that near the fixed point, when you calculate eigenvalues, it's an imaginary eigenvalue. Okay? So if you are more mathematical minded, it's just that has a negative real part and some imaginary part. So therefore, it's stable because it's convergent to the fixed point, but it oscillates, and it oscillates with decreasing amplitude, and that's it. So therefore, the plot of in time of I over N. Okay. So not without star. Okay. So you start very close to 0. You have an increasing number of infections, and then at a certain point this would be like this. So we had this with the SIR model. Okay. But at a certain point, the effect of having a replenishment of S will change this. Okay, so this will go this, and that it will again. Okay, let me try to be a bit better. Increase, and then all of this repeats itself. So if it increases, then you have again a certain depletion of the number of susceptibles. They will decrease, but then you have the replenishment, and the replenishment will make it again like this, and then always with a smaller amplitude, because the population at risk is diminishing because there are lots of immunity. Okay. But the dynamics between S and I will create this kind of thing, because they are oscillating. Okay, so that's still a different pattern that we had not seen yet. Okay, so one pattern was logistic growth for SIS. The other pattern was epidemic. Naturally goes away with large time number of infective people goes to 0, and in here you have again an endemic, but with recurring epidemic peaks. There's a recurrent epidemic peaks. Okay, yeah. Where's the mic? Mic. Yeah, okay, now you have to.
Okay, so this is just this model without the demography is the one that we saw that the epidemic eventually burns out. That's it?
Yeah.
And when you add demography, it doesn't burn out and it keeps oscillating.
Yes.
Okay.
Okay. Because it depends on gamma. Okay, gamma was 0 before. So it gives you the correct limit. Gamma is the natural death rate, okay, and which is compensated by the natural birth rate, which is this term, and here, if gamma were 0 with no death rate, which was the other model, this would be 0 and it's consistent. So, yeah, question.
I'm a little lost about the explanation. You told us that there's some value of
In English.
Okay.
Okay, better.
Okay. There's a parameter, specific parameter that turns a fixed point unstable, and then we'll have a catastrophic behavior.
but
What is the parameter? I just lost the
No,
explanation.
here we
sorry.
don't have this. Here this is a very well.
Okay.
We don't have a catastrophic transition. We have a smooth transition. Okay.
Okay.
Okay. Here. That's it. And that's all the story. All the
Okay.
story is this plot.
Okay.
Okay. It's not very complex thing.
Okay.
But yeah, you could ask yourself if are there cases where do you have alternative stable states in epidemics? Okay? And this you won't find this in any book of epidemics. But could you think about what could be a mechanism that could create two stable fixed points, two low endemicity or high endemicity, for instance. Okay. Any idea? This one is difficult. Yeah. Remember, we discussed two stable fixed point basins of attractions just a week ago. Okay? So, could there be some? In all of these models, there is no such thing. In all these models, what you have is the final is either goes to 0 or goes to some fixed point, or could keep on going oscillating. I will discuss this in a moment. So, so one thing is, for instance, in malaria here in Brazil, we have sometimes this kind of thing with some transitions. It is not easy to, but the point here is that most of the malaria, which is transmitted by insects, Anopheline insects, well, malaria is a protozoa that is a plasmodium, and plasmodium has many subtypes. And what we have here is mostly Plasmodium vivax. In Africa, you have Plasmodium falciparum, right? And which is more deadly. But here, the vivax has the properties that it can be in a dormant state in your liver. Okay? So it's tricky. So you can have situations where there are a lot of people that actually seem to be disease-free, but disease can emerge from out of nothing, let's say. Okay, but that person would be considered disease-free, and he is disease-free, but 3 years later, he becomes infectious. The person becomes infectious. There's an asymptomatic phase, and the asymptomatic phase you can have again the re-emergence. And this, if you write the models and so on, could create two stable fixed points, and then obviously then you could discuss how to avoid the one that you don't want, which kind of measures you want to maintain low endemicity and so on. Okay, now, very good. We have 3 different patterns. Okay. Now, I want to discuss the situation where there's loss of immunity. So somehow, if you lose immunity, then this guy. Then you have something like this, but without the gamma, okay? But without the interpretation that gamma is death rate, it's just this guy going here, okay? And these ones would not appear, okay? Because you only use immunity if you are immune, okay? So then you get this, then you will not have this one, neither this one, but you still want the population to be constant. And actually what we will get here is some plus gamma R instead of this, okay? Which will give you, again, a constant population, but just with this situation here. Where you have the loss of immunity. It's called waning immunity, right? And then it would appear here again. So I won't do this calculation, but it's a little bit, well, again, some fixed points and so on. But what you will get is the same thing here. I mean, qualitatively, okay? So it is the replenishment of susceptibles that creates the possibility of having this endemic state, and could be oscillatory or not, but in this case it's oscillatory. And in this case it's also oscillatory, okay? So, but with decreasing amplitude, okay? So, and actually this here, it's not necessarily a sinus cosinus, can be deformed like the predator-prey things, okay? So now let's think what we know about recurrent epidemics in our life. Tell me, which disease is recurrent? Which disease that we have in our society which is recurrent? Measles, no, measles is not recurrent. I mean, it has almost been eliminated, but not completely, but it's not recurring. Dengue. Dengue is seasonal. Yes, you are right. But this is, yeah, okay. So there are many ways of being recurrent. Okay, many ways. One is just seasonality. Okay, so dengue it's a disease which has to do with the climate and the temperature and the humidity and many other things also. But there's the variation of the climatic drivers, and then you have the seasons where you have dengue, actually, where you have the mosquitoes and when you have dengue. People could think that, okay, so let me propose a puzzle, okay? This is also the same thing as for malaria, okay? Malaria, vector-borne diseases, if the vector is affected by temperature, and if it's a mosquito, it's always non-temperature regulating, and maybe it's also connected to humidity. Humidity can have also connection to rainfall. It's not the same, but could have. And rainfall, for the case, for instance, of dengue, creates more places where the mosquito can breed, and therefore there can be a connection, okay? So, but this is, we are talking only about the mosquito, okay? So usually you would assume if I have the mosquito, I will have dengue or malaria, okay? So, but when you go for data in certain regions, for instance, if you go for data in the south of Brazil for dengue, where it's very few cases, or even if you go to Rio de Janeiro, the peak of the number of mosquitoes does not correspond to the peak of dengue. Okay? And for malaria, if you do, that's a work that I actually made with collaborators. And malaria, for if you go from the northern part of Argentina, then you have a region where it's not, I mean, has been controlled, but back 10 years back, there were some cases still in the northern part, near the border with Bolivia, and there were cases of malaria. Okay? And then there were people that have made studies about the mosquitoes, and then you have a difference between the season of mosquitoes and the season of malaria. So why do you what do you think that this happens? Why is there a difference?
One hypothesis, I think it's not the case, but could be incubation time.
Incubation time. Yeah, but dengue doesn't have a long incubation
Yeah.
time. Okay, that's not the mate. But yeah.
A second hypothesis would be that at first we have few mosquitoes, so we have few people infected. The number of mosquitoes grows, and the number
The
of
number of
people
mosquitoes is in equilibrium in this case. I mean, you don't have the introduction of one mosquito and the population dynamics of the mosquitoes.
Oh.
They are already there and they are oscillating. They are not small number.
I think what we are discussing is that we have a peak of mosquitoes, and then we have a peak of disease later. Is
Yeah.
that? So
And
I think it's because at first we have less mosquitoes and less people infected. The number of mosquitoes grows, the number of people infected grows, and then we have a lot of mosquitoes, and then they become infected, the mosquitoes, and then only then they transmit to people.
So, okay, could be, but for instance, there are places where you have the mosquito and you don't have malaria. And there are places where you have the Aedes aegypti and you don't have dengue. How can you explain this? So this is easier. Why can you have the mosquitoes and don't have the disease? And no cases.
Yeah, there are no pathogens to the mosquito get infected to, like.
This is unlikely that nobody. I mean, if you are in Antarctica, it's correct. But we are very distant from any place where people go and could be infected. But it's unlikely that over the years you wouldn't have at least one case of a person being asymptomatic carrier, for instance, that would, in principle, could initiate an epidemic. Okay? So, yeah.
There is also the susceptibility in the population. There are some phenotypes that have different kind of emissions, I think, and they present different susceptibility to the pathogen. So this also can change the infection.
Yeah. So, okay, but near the border regions, the populations are more like the same. Okay, from the human populations are more or less the same. The mosquitoes are also the same. And why are there places that there is no although I have the mosquitoes and I have no disease at all? Okay, you and then you.
Yes, maybe could be because the parasite is just adapted to one species of mosquito, and the thing is that you have competition between species of mosquito. Aedes aegypti is a really aggressive species, so it tries to displace the Anopheles mosquitoes. So what happens is that
this happens, but not in this area. Okay, this happens. This can happen. So biodiversity and competing species, which compete for your blood, could suppress the effective biting rate of the mosquitoes on humans, because there are all humans take action to protect themselves, and then this is actually the case of the Atlantic forest here. I mean, it's probably it's one of the explanations. You have the forest, and you have some anopheles also, and so no malaria, almost as a residual cases only. This could be this, but there could be other explanations. Yeah, you had a.
Well, I think the social conditions can be impact, especially in the vector-borne disease, because when you don't have like good conditions and basic saneamento, I don't know how to speak this in English, but
sanitation.
Yeah, sanitary conditions. This could influence the vector.
Yes, but this would influence more the population of the vector. I'm saying that there are conditions to be there, that the vector is there. Okay? So sanitation is very important for certain diseases, for instance, cholera. Okay? So I was once talking to a person from Rio de Janeiro who has written a model for cholera dynamics, very interesting. I worked with this model also, but this was back in the 90s. And then when I met her, and I said, "Oh, you still work with cholera?" "Well, there's no cholera." Disappeared from Brazil, disappeared. Why is it disappeared? Well, infrastructure and sanitation, so it disappeared. So no cholera, no. But for dengue, yeah, there's sure the importance of having conditions that will be good for the mosquitoes. But I mean, what I'm saying is there are good conditions, but still there's no disease.
Maybe the two options could be like immunity. So, but I don't know if it immunity, like the population is immune, or maybe they are not making tests. So they don't know if the disease. If you don't do tests, there are no cases.
Okay. Yeah, that could be. But well, malaria is usually usually tested. Okay, you could have what you're saying is I have a hidden epidemic. It's a secret epidemic. But well, there is no data showing this. And actually, if you go for the places I'm in, there's a border between where you have the epidemic or not. So there's more uniformity in the testings between the places and so on. Because this would imply that they have tests at a certain part and don't have tests going further south. But this is not usually true. Right.
I don't know if that... in which the humans are not the main source of food of some mosquitoes, and there are other fauna that there is. So there is a protective effect of it.
This could be, but this is again related to the amount of mosquitoes. Okay, but okay, they could have preference for orders. Okay, but mosquitoes don't have very strong preferences in this case. And but yes, if you have a region where you have other animals, then at least a certain amount of the bites will go for the animals. They also have blood, right? So for instance, the Anopheles doesn't care. It's just blood. So this can create a sink because this malaria is co-evolved with humans. It's a very complex cycle. It's a protozoa, and if now an infected mosquito bites, say, a pig, the pig will receive the plasmodium, but there is no cycle there. Okay, so it's a sink. Okay, so again, biodiversity things and so on could explain something. This is usually invoked also for the Atlantic forest. Okay, and also for situations in some parts of the Amazon where you have mosquitoes don't have cases, and it's usually connected to this kind of thing. Okay, so there's one you on your. Yeah.
I don't know if this makes sense, but maybe it depends on the dynamic of the mosquito population. How well established is the population of mosquitoes in a place? Because if it is seasonal, the mosquito population, and we assume that the people are traveling, maybe they're going to start reproducing, and it is going to be easier for the increasing population of mosquitoes to have to have the disease. But if it is a population that is always there, maybe it is a different case. I don't know.
So let's do this for you. Let's go for the cycle of the disease. Okay, so you have an infectious mosquito. So what happens? It bites some human. Okay, so there's a probability that the person gets infected. Say the person gets infected, and what happens then? The person, there's an incubation time, and the person gets sick. Okay. Okay. So then you have a non-infected. mosquito that comes and bites this person, probably in the early stage when the person doesn't know he's infectious and blah blah blah. And what happens next? The mosquito gets infected, and there's an incubation time. Okay, that's called the extrinsic incubation time. Extrinsic incubation because it's extrinsic to humans. Okay, so there's time also in the mosquito. Now, how long does a mosquito live? Okay? So if metabolism of mosquitoes, which are do not regulate temperatures and so on, will depend on the temperature. Okay? Yeah. So it's the temperature will be kind of a clock. So higher temperature, metabolism goes faster, everything goes faster, and when you have lower temperatures, then you will have a slower pace of metabolic. Okay, so what can happen is that the extrinsic incubation time will depend on temperature, but also the lifespan could depend on temperature. But the extrinsic incubation time depends strongly on temperature. If the temperature is low, the incubation time, the extrinsic incubation time would be maybe longer than the life of the mosquito. And therefore you don't close the cycle. The mosquito dies before being infective. Okay? And so this is one possible explanation. Right? Okay, this is an explanation also that you don't have, for instance, malaria and dengue in the very south of Argentina or on the northern part of Europe or Canada and so on, because, well, you cannot close the cycle. But near the border, you can have certain regions where, because temperature is oscillating, you can have this kind of situation where there are years where you have mosquitoes and you can have, say, dengue or malaria, because it was, I don't know, maybe a hot year, the temperature is fluctuating, and also the humidity can come into the equation. And then other years, no. Other years that are colder, maybe then you have the mosquito, because the mosquito is there producing. It is just that the mosquito, but or either the virus or the protozoa has a certain cycle in the mosquito's body, and well, then it goes, doesn't become infective because the mosquito is already dead. So this is one possibility. Okay, so good. Next is water. Okay, let me this here, the SIR model. Now, I wanted to discuss a further situation, which is a little bit different, although it's not so different, which is sexually transmitted diseases, and I will concentrate on gonorrhea. So, the first thing is my population at risk is only the sexually active population. Okay, it's not the total population. It's the sexually active population. And we will ignore, for simplicity, I'm not saying it doesn't exist, that there are men that that have sex with men and women that have sex with women. We will consider population which is heterosexual, but okay, no prejudice about it. It's just for modeling simplicity. Okay, So why is this important? Because then I can say, okay, I have a population that has a certain number of males and a certain number of men and women, males and females, and the infection comes from the contact from one population with the other. That's why I'm putting out the homosexual relations. Okay? So what you would have is what people could say a crisscross thing. Like you would have, say, S, I, and R are males, or if you want men, and S star, I star, R star is the females variables. Okay? So I would have something like this. S can go to I, which could go to R. Okay? And S star can go to S star, goes to R star, but the population are connected, and S goes to I only through the contact with I star. And S star goes to I star only with the contact of an infectious male. You have a crisscross. Okay? So two populations, and the same population doesn't infect itself. And then we have this. This model, if you develop this, that will give you typically SIR model dynamics with the population at the end, zero infectious and so on. No emotions. Now, gonorrhea doesn't give you actually immunity. Why are?
Why are we considering this model and not coming back to S?
Yeah, that's what I will do. Okay. So, you have usually a time when the person has been treated, in which the person is effectively recovered. But this time may be small. Okay? So, and once the person has finished its treatment, the person will be again infected. So it is a very short duration for immunity. Therefore, it is easier. We would say this, okay, here and here. But we don't need to complicate. If the time spent here is small, then we can go directly from here and here and just don't consider this, okay? And don't consider this one. Okay? So this can go back here, and this can go back here. Okay? So this is an SIS kind of model, okay, which with this crisscross infections. Okay? So this kind of situation is not very difficult to model. We will consider that the population size of males and of females, of men and women, is constant. Therefore, I will use that S. So this guy doesn't exist anymore. S star plus I star will be some n, and S plus I will also be some n. Okay. And then, if I write down the equations, I will write down only the equations for the infected, okay? Because, well, no infected gives me S, okay? But I know that the infective, say, will have something like this. There will be some beta or some R. Let me write some R. Okay. Times the number of susceptibles times the number of infected of the other populations. Okay? Minus some mu times I. Okay? So the copulations are coupled. So the equation for S would be simple. Let me see what I'm doing here. Oh no, this is not correct. Let me. There's no. It's better. Sorry, I will write all the equations. It's better. I wanted to make a jump, and I ended up. Okay. And this gets some plus mu I here. Okay. Di dt will be okay. R S I star minus mu I here, and then you have the corresponding equations for ds star dt, which should be minus R star, okay, times S star times I, okay, plus some recovery from infection, which would be plus mu star times I star, and di dt will be R star S star times I minus mu star times star here. Star here. Okay? So now look at these equations here. Okay? So I wrote this R here, okay? And this is a little bit tricky. Okay? So this is an SIS model where the infection comes from this crisscross, from connection between two populations. The rest is just the SIR model, SIS model. So we had an N here, yeah? Previously. We had an N. Why? Because we wanted the situation to be frequency dependent. So now we have N star and N. So if I go for this equation and divide by N here, I get the frequency susceptibles. Here I have the frequency susceptibles. And here the frequency of infected. If I had an N here, I would have problems. Okay? In principle. Not could have or not. Because if I had beta N, okay, then I would have I star over N. Okay? Which is the frequency of it's the it's kind of you take the population of females and refer to males. It's kind of crazy thing. Okay? So you could also have put here something like okay, then I put N star here. Okay? Could be. So I will discuss then the results, and so we will leave the R. Okay? Leave the R. So if you leave the R, and then you can do this elimination of S, and write in the equations for I. Okay? So I don't care anymore about the S equations. I care only about the I equations. So we'll have easily ds dt is equal to R times I I dt is equal to this here, N minus S minus mu I. Okay? So di star dt will be R star. So I'm considering that the probability of infection can be different from one to the other, which is true for gonorrhea. Okay? These guys are R star and R, which are the infectious rate of this kind here and here. This is a woman infecting a man, and this is a man infecting a woman. And the probabilities of that the sexual intercourse produces a new infected one is dependent of if it's the man that's infected or it's the woman that's affected. Okay? So that will be this. So these are the equations, okay? And oh no, n minus I star. Okay. So these are two equations which are connected, both of them, which have some nonlinear terms and some. So it looks like a little bit logistic, but it's not exactly, okay? Because this has a star here, and here you don't have a star, you have a star, so you have I star times I, okay? So these are the equations, and then you can go and try to find the invisibility criterion. Okay? In order to do this, what do? You will do the following. You consider that the population of infected is small, and I will discard, I will neglect the terms which are multiplication of two small numbers, I and I star. Okay, so I take only the terms that are linear, not the non-linear. Okay, so in this case, we will have di dt is equal approximately to r times I star times n minus mu I, and di star dt will be r star times I times n minus mu star times I star. Okay? So at the very beginning, when the infected population is very small.
Professor, why would we disconsider I multiplication by I star? Couldn't it be a large number if the epidemic was?
No, we are modeling only the start of the epidemic.
Ah, the start. Okay.
Yeah, we want to know if we have small infections, if it will grow or not. That's the only thing that we want. Okay, we want to know if it will grow or if it will not grow. Okay. So now here you don't have you have a coupled system. Okay, it's not like the ones with SIS and SIR, where effectively I could get an equation closed condition only for the a system with having only one equation for the infected. Now we have two types of infective which are connected. So this requires a little bit more mathematics, but this is very similar to what we did with Volterra. So this is a linear differential equation. Okay? This is linear. All terms are linear. It's coupled. It's a system of two linear coupled differential equation. And I can do the famous guess. Okay, the guess would be I some a e to lambda t, and I star equal to b a to some lambda t. Okay, you can say it's a guess, that it starts exponentially, but actually there's theory saying that this is true. Okay, that you can have the solutions of these equations in terms of these exponentials. Okay, and now we want to know the sign of lambda. If lambda is positive, you have increase of infections. If lambda is negative, you have decrease, and the infection does not invade the population. Okay, so we are interested about the positive, if lambda is positive or negative. So doing this, in these equations here, it's nice because what you get here, you get A, the first term will be A here, times lambda times e to lambda t. Okay? That's the, just derivate this thing in time. And this will be equal to r times r star, which is b, e to, okay, I'm looking at this, okay, b times n, b times n, e to lambda t, okay, this one, minus mu times a, e to lambda t, which cancels everywhere. Okay, and then I have a is equal to a lambda is equal to r b n minus mu a. Okay?
Professor.
Yes.
Can you repeat why you're doing this? I think I lost something.
So we want to know the stability of the disease-free equilibrium. Okay, I have a population that has no disease, and I introduce a small population of infections. Okay, and I now want to do the same calculation I did with the other models, which is I want to know if the number of infections will increase or not. If it increases, then you have an epidemic. If it decreases, it is very small, and it decreases, goes to 0, you don't have epidemic. Okay, so that's the calculation. First thing is, if I have a small number here and a small number here, then this is much smaller than the other ones. All the products of i's can be neglected. I get this equation. Now, this equation has only linear terms. And when you have only linear terms, you can always find solutions which are in this form. Okay? So I have some constant e to lambda t, b some constant e to lambda t. Now, this is what? This is it's modeling the initial exponential growth of a population if lambda is positive. Okay? So, but we don't know lambda. We have to determine lambda. Okay? So, and if lambda is negative, then you don't have any epidemic. So in order to do this, I take this and I substitute in these equations. I get a times lambda times e to the lambda rbn minus mu I, which allows me to calculate a in terms of b and lambda. Okay? So where did I leave my equations? So this gives you a times lambda plus mu is equal to r times b times n. Okay? Which gives you that a is equal to b times n divided times r here. There's our r here. R divided by lambda plus mu. Okay? Good. Now I have to look for the second equation. The second equation, if I star is given by this and I is given by this, I can calculate this, and then I have lambda times b e to lambda t is equal to r star times I, which is a to lambda t times n minus mu star times b a to lambda t. This cancels. I have lambda times b is equal to r star times a times n. Okay, here I missed it is a star. I lost the star. Okay. Minus mu star times b, and that's the equation. But now I know I a, so lambda b. Okay, Yeah, lambda b will be r star times n star, but then I know that this gives you r, b, n. R times b times n divided by lambda over mu minus mu star b, which is an equation for b. Or no, it's not an equation for b because b cancels, okay? And it becomes an equation for lambda. I multiply now everything by lambda plus mu. So I will have lambda times lambda plus mu is equal to r star times r times n star times n minus mu star. It's quadratic polynomial, okay, which will read lambda squared plus the terms in lambda is lambda mu. Here you don't have anything. And here, this goes here, so they sum up here. Minus r star, r, n star, n equal to 0. And we know how to solve this, okay? So, we know how to solve this. This gives you lambda is equal to minus mu plus mu star. Plus or minus are this thing, mu plus mu star squared minus 4 times. Is there something wrong?
It's too fast.
I lost something here.
Me too.
I think mu star needs to be multiplied by lambda plus mu as well. Because when you multiply everything by lambda plus mu,
sure. I forgot to multiply here, okay? So then you have the term that was mu star times lambda here, okay? And then you have a mu star squared here, okay? Is this correct? I have multiplied by lambda plus mu here. What I had here is correct, minus mu star times lambda plus mu. When I pass all of this here, I have lambda this, I have this. This term was negative, becomes positive. Then you have this term which gets positive, and this term which was negative becomes positive, which is mu times mu star, and is's have to be 0, okay? Okay? So I had forgotten one term here. So the square, the roots of this polynomial is this plus this minus 4 times what? Mu star minus r star n star. Okay. Question?
I'm sorry. Why is there a minus over there after you replace the a? Like on the third one?
There are what? This is correct. Yeah. This is minus. Here there's no minus because it's the effective term. Then when I multiply
on
all
the third equation, you have the r thing and n thing minus rb, or what is that?
No, this is multiplied here.
Oh, thanks.
It comes from this substitution here. Okay. So we are coming to the end of the story, which means the following. Okay, this here, we want to know if lambda is positive. Okay. So in order to be positive, this thing here has to say overcome this one. Okay, this is negative, and I'm adding something which has the square root, the square of this thing. Okay, and then there's this part. So this part has to be negative. Okay, then you'll have this. This one is the square root of this, and if I add something, then this gives you a positive lambda. Okay, otherwise not. Okay, so we really need that mu star is smaller than r star, n star. Okay? Therefore, r star, n star divided by mu star has to be larger than 1. This is r0. Okay? So, look what happened here. This is the R0, and this is a product of things which depend on R and things that depend on stars. Okay? So that's like the product of two subtypes of R0. Okay? So now this, and here again, if I had supposed that R is divided by either n or n star, at the end there would be no modification because you would have some beta and some beta star without the n's. Anyhow, they would cancel anyhow. So I don't have to care about the normalization of R here in this equation. Okay, so very good. So this is something like they can think that this is only connected to males, and this is connected to females, and this is the maximum. That's the number of infections that every male creates. And this is the number of infections that every female creates. And then you have to multiply them, and this has to be bigger than 1. Okay? So another situation where you would have this kind of thing is if you had not males and females, but you had two species. For instance, humans and vector-borne diseases, mosquitoes or whatever, any bug. Okay? Then you also have this criss-cross thing. Okay? The humans get infected by mosquitoes that are infected, and the mosquitoes also have this criss-cross. It's more complicated to write this for vector-borne diseases. It's a little bit, you need more things. This is the simplest case of criss-cross and allows a calculation. But also, if you do for vector-borne diseases, simple vector-borne diseases, you will also have something which is the R0 of how many mosquitoes one human infects on average, and this one would be the number of humans that are affected by the by one mosquito. Okay, so there's a kind of separation. Yeah, there's a question.
Is it possible to consider two different values for lambda? I mean, one for I and one for I star?
You will get the both. For consistency, we will get lambda equal to lambda star.
Okay.
Okay, if you do the calculation. Okay. So I already started with lambda because I know that it would be a subproduct. Okay. Okay. So these parameters we can think of actually maybe measuring them, because that's the average number of infections that the male creates, and the average number of infections that the female creates. Okay? So there have been studies in the 70s in US trying to establish values for this. Okay? And what happened is that this part for the man is smaller than 1, and this one is bigger than 1 for females. Counterintuitive, yes? So the number of infections that every male will originate is on average smaller than 1. But the number of infections that every female would originate is bigger than 1, and when you multiply them, it's bigger than 1, marginally, 1.1, but it's bigger than 1. So, explanations. Why is the number of secondary cases that a woman originates bigger than the secondary case that a man originates? It's curious, yes?
Professor, I think females generate more infections on average because in sexually transmitted diseases, the disease is transmitted from body to body, like surface area to surface area.
True?
Surface area to surface area. Like through sex, there will be a very small, how to say, very small feridas that will transmit the disease.
Yeah, but this can be transmitted in either way.
Yeah, but women they have a larger surface area in their genitals.
Well, I mean, this could be. I don't think this is the Ayers thing is an explanation. Okay. So other explanations.
Maybe because in difference of metabolism, women have a higher load of pathogens.
The woman has a low. Well, I don't know the answer if this is true or not. The metabolic and the viral load, I don't know. Okay.
Thank you.
And it's not a virus actually; it's a bacteria. Anyhow.
Thinking maybe morphologically, like for the males, they can see the genitalia, so it's easier to see if there's something wrong, if they're like feridas and everything. And for the females, since it's something that is not exposed, it will take a little bit more time for them to realize they are transmitting.
That could be one thing. That could be one thing. Okay, more speculations?
For me, the simple explanation is that, for me, the simplest explanation is that women have more sex than men in this case.
So, that is the obvious explanation that people would say. This thing is proportional to the contacts of everything. So that's, but actually, if you go for surveys, it's not true. Okay? You can, this is, people from demography, they do this kind of thing. And it seems counterintuitive here first because they say, oh, well, this is easily explainable by something which is just women have more sexual intercourse, but if you go for the data, it's not true. Okay, so there's something else. So. Maybe others think?
Yeah, my idea is kind of related to them both. That is like the contact with a woman is more likely to produce another infection because the contact with the woman looks like more intimate, looks like a biggest exchange of material. And another part that is I don't know in the other disease, but in the HIV, I read a paper that was talking about the importance of the cleaning of the area, and like the man is more likely to clean the area because it's easier in the fastest moment. So it's are decreasing the population of males that are contracting HIV because people are just washing the thing.
So I don't think this is true, and for gonorrhea, but there is a part that is true. That is actually, it is true that, okay, if you look at this, okay, so here you have the populations here, and then you have fixed numbers, okay, and what you could have something here just because of this being larger, and it would be, but okay, you know the sex ratio, okay, it's almost 1/2, okay. Almost very small, but this cannot explain, and different sex ratios could be an explanation, but you know the sex ratio actually in the population in general, and this is only active sexually, okay? But, wow, okay. Anyhow, this cannot explain. But then you have the R, and the R has some probability of transmissions times the number of contacts, okay? So one hypothesis has been number of contacts different, but number of contacts is not different if you look for the data. But then you have still the probability of transmission being different. And what happens is that what happens is that that women, so it's very complicated actually. Yeah, women have a lot of asymptomatic cases, or oligosymptomatic, or almost no thing they can see, than men. So then you have this transmission due to a higher number of asymptomatic cases, and this can explain here the difference, okay? That's more like, it's more biological explanation. It doesn't have to do much with the pattern of sexual contacts in this case, okay? But sure, you can do something much more refined, because you know that these models assume that the population is well mixed, okay? But then you may have super spreaders, and this has not been taken into account here, okay? So that could modify the result in principle also, okay? Now, question: how do you think you could model the existence of super spreaders? Or super spreaders are people that have a very high active sexual life. Okay, how would you model this? Ideas?
Maybe can introduce a new class on the model.
Yeah, you can. So there's the old way and the new way. So the new way is you try to have the network, but I mean, having the network is like gold. Nobody has networks really mapped. Okay, there are some studies. There's some study from Colorado which is very famous, and so on, and so on, and so on. But it's very particular to a place. You don't know the rest, and how do you survey this? Because, you know, people lie. So, and if you take at face value the things that you see in the newspapers, everybody's having sex all the time, okay? Which is probably not true, okay? So it's difficult to build, okay? But sometimes you can do simulations with the stochastic dynamics where you don't need actually on the whole network. You need only, for instance, the distribution of degrees in the network. And this is likely to be more constant. And you have, for instance, in UK, you have surveys of this. And then you have the number, say, with the the number. What you have is the number of sexual partners a person has a year, and then you see the frequency. Most of them have only one, and so on. And this, then you say, okay, as this corresponds to sexual relations that actually link nodes, where the nodes are the people, so therefore this is the degree distribution. And if I have the degree distribution, I can do a lot of simulations, and I can have, for instance, I could have a degree distribution where there are people that are super spreaders in the distribution, which will be kind of heavy tail or something, okay? But this is the new way, the standard way today, but the old way would be following your suggestion, which is very, very, okay, I'm over time, but it's, I won't do any calculation, okay? So don't be afraid. I just want to write things. You could subdivide your population. So you are not you're not a fan of networks. So what would you do? You'd say the males, okay, would be divided into S1, which is very active, and S2, which is just active. Okay? Or you could have more structure. S1, people that have more than 50 partners a year. S2, more people that have between 30 and 50. S3, people that have between 10 and 30. And then you have between 5 and 10. So you can do this with a lot. I will do only with 2 in order not to write a lot of things. So females have the same thing. Very active and active. So let's write just one of the equations, like ds1 dt, okay? So ds1 dt will be something like -1, but then it can be infected by either well, there will be the I stars, okay? The I and the R's are, I is also subdivided by index 1 and index 2. So as this comes only from the females, from the star variables, then there will something which will be proportional to I star 1 and something which will be proportional to I star 2. But then you can have a probability of infection given contact, different here, let's say R11, then from here R12, but then there's still another thing. So what is, for instance, this is very active, okay, the new person. On average, every very active has more contact with just active or more contact with also with the very active. So the contacts have to be divided between the two classes, okay? Okay? So you have to put here the contact rate between this guy, the very active females and the very active males, which I will use some alpha 1,1 and here alpha 1,2, okay? So this is as this would look like, and then you have all the other terms. I don't want to write this. But you see here that when I will write S22, there will be R22, R21, alpha 1,2, and alpha 2. So you have this matrix of alphas here, which is which says that from all the proportions of the contacts that a very active person has with also very active female, opposite sex, and very and just active. Okay, so this is a contact matrix. Okay, and if you have more compartments, larger matrices. So this you can try to evaluate this, and you see that the dynamics should be pretty much different. If, for instance, very active have a lot of partners that are also very active, you tend to have a very high incidence and very active population. You have incidence in the active because there's no exclusivity. And the active to the active has also contact rate. You don't need to be very active to have an infection. And obviously here this can depend also on the number of contacts. The very active has more contacts or down, so on. So this matrix here will be very important. Okay, so what you would need in this case, instead of having in the case of networks, you need the distribution of the number of partners. Here you need the characteristics of contacts between very active and just active populations. Okay? So this can also be surveyed by people from demography and so on. You can have this kind of situation. So you have the contacts in this case. So, okay. That's all for today. Friday we have a free discussion as usual. If you have questions, please leave them in the box. Let me see the boxes. There are things in the box, I don't know. Okay, there's nothing, but there's still one day for you. So see you on Friday.